Okay, here are our quick notes for the unit on solutions. Okay, so first of all, what is a solution? A solution is also known as a homogeneous mixture. Okay, to get a solution, we need to undergo dissolving, which is a physical mixing of solids or gases into liquids that make an even distribution. So our solid liquids, we call them the solute, and the liquid that dissolves them, we call them the solvent. Okay, so if you have our water here as a solvent and we drop in a solid sugar cube, as it dissolves, we can make that sugar solution. Okay, another way of looking at it is you have your water solvent and your little pieces that are evenly distributed are our solutes. Okay, now most of the liquids we use in our daily lives are not pure liquids, they are solutions. Okay, besides distilled water, pretty much anything that we drink is a solution. Orange juices, pops, sodas, beers, anything like that is. Gasoline's a solution. Most of our cleaning, all of our cleaning materials, all our soaps are all solutions. They are not just single things there. Okay. Now this dissolving process, when we dissolve, the solvent has to collide with a crystal. It has to collide with those solids. This then attacks things from the edges and the sides of that crystal. Okay, and when that happens, the solvent then attaches itself to those crystalline particles and pulls them apart, and that is what creates dissolving. Okay. There are different ways we can talk about the speed or the rate of dissolving. So we can make things dissolve faster or slower. So the first thing is particle size. So if we can make the particles smaller, we can have them dissolve faster. If we can make them larger, they will dissolve slower. Okay, so something crushed up like this will dissolve faster than something that is a big like this. This would have more surface area, less surface area. In terms of temperature, the warmer the solvent will be faster and the colder will be slower. So hot water, you can see here, is less left. It's already dissolving faster. Cold water will dissolve slower. And then if you stir something, it can make it dissolve faster, or if you don't stir it, it comes slower. So again, stirring A would dissolve faster than this. Believe it or not, stirring is our biggest effect of all of these things inside of here. Okay. We also can talk about how much can dissolve. So one is about how fast, now how much. The term we use for how much is solubility. That's our limit. Okay. It is a number like density. So what is the solubility? So like, for example, the solubility of table salt is 35 grams per every 100 milliliters of water. We can't dissolve more than 35 grams and then in 100 milliliters of water. It just does not happen. Okay. If you dissolve that maximum amount, we call it being saturated. Okay. If you dissolve less than the maximum solubility, it's called being unsaturated. If you dissolve more than the maximum, which is kind of a special scenario where you can only do it at high temperatures, you actually can get something called supersaturated. Okay. Now, within solutions, we can change the solubility. So there are two ways we can actually affect how much can dissolve or its solubility. First of all is temperature, okay? So with temperature, if we have solid solutes, okay, if things like salt, sugar, minerals, those kind of things, if we warm them up, their solubility goes up. If we cool them down, their solubility goes down. So this is a direct relationship. You will see on this chart that in all cases, as the temperature goes up, all the solubilities on the right-hand side also go up, okay? So solubility is directly related to our temperature. Notice how I don't say proportional here because they definitely do not all go the same way. Some curve, some don't curve, so there are different things for that. For gases, it's exactly the opposite, okay? So like carbonation in pops, oxygen in water, those things are different. The warmer they are, the lower their solubility. The colder they are, the higher their solubility, okay? So this has an inverse relationship, okay? The reason why, well, when you warm up solids, they get more energy, and with more energy, they're able to dissolve easier. For gases, if you give them more energy, they actually can leave the solution easier. So the increase in energy by warming them up helps solids get more soluble and makes gases less soluble. So what are some environmental impacts from this? Okay, well, salts, minerals, and sediments, they become more soluble. Okay, so if you warm up water, we can get more minerals, more sediments, more fertilizer into our water, which then creates a different type of plants that can grow there. It creates different amounts of salt that can be stored there. So literally the temperature of the water can change what animals and what plants thrive or grow in certain areas. The exact opposite is true for oxygen and carbon dioxide. So for oxygen and carbon dioxide, if we warm them up, it becomes less of it. So again, if we have less oxygen in our water, different fish and different species of animals and plants can't live there. So we can change how active the water is or how viable the water is for living for our oceans and our plants. Now, the Black Dog Power Plant is a good example of that. That power plant down in Bloomington there, they warm up the water from the Minnesota River, and they have actual ponds that help make them cool them down before they allow them to go back in the river to stop this pollution from happening. So with solutions, we also can measure concentration. Now, concentration is a word for the relationship between solute, dissolved, and solvent there, okay? If you are concentrated, you have a high amount of solute. If you are dilute, you have a low amount of solute in comparison to the solvent, okay? We can represent these as numbers, so like 233 ppm, which stands for parts per million, or 3.454 grams per 100 milliliters of water, or 2.5 moles per liter, okay? Notice how they all have a per in them because it is a ratio between solute and solvent, okay? The bigger that number, the more concentrated it is. So 3 moles per liter would be more concentrated than 1 mole per liter. 2,000 parts per million would be less concentrated than 5,000 parts per million, okay? So the bigger the numerical value, the more concentrated it is. There are 3 ways we can see this in our lab or in solutions. First of all is the number. So if you can look at a number, and the bigger the number, the more concentrated it is. So you go from 0.1 to 1 to 10 moles per liter. This is the most concentrated, this is the least. You could look at it visually, where the more concentrated something is, the darker its solution will be. Now, if there's no color to the solution, you can't see it. But here we have a really light solution. Here it gets darker, here it gets darker. That comes from being more concentrated. You could actually look at it through the atomic level, where the number of solutes, the purple ones, would be less. Here it's a little bit more, here it's a lot more, okay? So we can see that this would be our most dilute and our most concentrated in our things. So 3 different ways we can actually see this or determine it. In chemistry, we have one favorite way we like to record concentration. It's called molarity, okay? We symbolize it by a capital M. And molarity is the concentration of moles of solute dissolved per liter of solution. Now remember, we've talked about moles before. They are those packages of atoms that we use to represent amount. So instead of doing individual atoms at a time, we actually group them in sets of moles, okay? So to find the molarity of a substance, you would take the moles of your solute, you'd have to divide it by the liters of your solution. So it'd be moles per liter here, okay? So basically it's moles versus the volume, and the volume we always use is liters, okay? So what's the molarity of a solution if you dissolve 1.25 moles of salt into 3 liters of solution? Well, here's our equation. We plug our numbers in, and we would get a molarity of 0.417 moles per liter. You could also label this with a capital M. That is also acceptable. So then what is a dilution? So if we have concentrations and can change the amount of solute and solvent, we can actually find ways to dilute it or make it less concentrated, okay? So when you make it less concentrated, we do that by adding solvent to our solution and do not add any more solute, okay? So here would be an example of a diluted solution. Here would be an example of a concentrated solution. So when have you created a dilution or seen it done in your life? Possibly when you have mixed like juice. You may have got concentrated orange juice and put it in and then dissolved it and then diluted it. It's possible that you use like that Mio stuff in your water that comes in really concentrated and you put it in with your water and dilute it. It's possible for like laundry detergents. Sometimes you dilute those. So lots of different ways that we've diluted. Usually what happens is you're only adding water, okay? There is a mathematical formula for dilutions also. That tells us that the molarity times its volume that we use will equal the new molarity or the new concentration we have times the volume that we end up having. So M1 V1 equals M2 V2. Again, our 1 stand for initial or the start, and 2 stand for the end of these things as we go through and dilute them, okay? So here's some dilution practice. Here we have concentrated 12 molar HCl. We want to make 250 milliliters of 3 molar HCl, okay? So we want 250 milliliters, that's 3 molar. So this is what we want at the end. This is what we had to start, okay? So we start with the concentration of the start, or the concentrated, is 12. We don't know how much of this we're going to use. We want to make 3 molars and 250 milliliters. So by plugging this in, we can then solve for V1, and we get 62.5 milliliters. Now, if we want to make this dilution happen, this is how much of our initial concentrated stuff we need to have. But we wanted 250 milliliters, but we're only going to use 62.5 of the concentrated. So to get the water, what we want to do is we want to take the total water we need, the total volume, minus the stuff for the concentrated. That tells us how much water we're going to need, okay? So the total is 250, or V2 basically this is basically V2 minus V1 gives us our water, okay? Here's another example of a problem. We have 3.75 moles of this in 0.5 liter solution. What's the molarity? So here again we see molarity concentration. So our first step here is to find the molarity. It's 7.5. So how many liters of 0.25 molar solution can you make from this stock solution? So it is 0.75. How much of this can we make? We have a half a liter. So again, we have 0.75 molar. We have a half a liter of it. This is what the concentration we want to make. What volume can we make? Here we solve for V2. We can make up to 15 liters of this.